going to be going over the chapter review for Chapter 9. As always, we will begin by saying what is the operation and what is the rule for that. And so we look at number 1 and say, okay, what's the operation? The operation is addition. To add or subtract, the names have to be the same. In algebra, we call them like terms. When you add or subtract, the name stays the same. So the name is square root 7. 8 of those plus 5 of those makes 13 of those little square root 7s. Any questions on number 1? Number 2, we begin by saying what is the operation? The operation is multiplication. What is the rule for that? Well, the names do not have to be the same. It's okay if they are, but they do not have to be the same. To multiply, we have a little two-step process. We multiply the numbers. 8 times 5 is 40. And you multiply the names, and you get a new name. And when you multiply with like bases, you add the exponents. But when we multiply radical names, we just multiply. Square root 7 times square root 7 is square root 49, which we understand could have been written as square root 7 times 7. What we see there is that we have a pair of 7s, and from that pair of 7s, you would bring out a 7, and there would be nothing left in the radical. If we wrote it as square root 49, we would say what times itself equal 49, and the answer is 7. So square root 7 times square root 7 is square root 49, which is 7. So we're going to have 40 times 7 in this case, and 40 times 7 is 280. Any questions on number 2? Number 3, what we learned to do way back on page 5 was to divide or reduce the numbers, divide or reduce the names, and we'll get a new name. And when you divide with like bases, you subtract the exponents. So we did our numbers with our numbers and our x's with our x's, and we'll do our y's with our y's, and we'll do our radicals with our radicals. Now we got to be careful, because the only thing that subtract the exponents applies to is when you're dividing like bases. Remember, we said we're going to multiply the numbers and multiply the names and get a new name. And when you multiply with like bases, that means when there's exponents that we're dealing with. Only 2 of these scenarios are we dealing with exponents, the x stuff and the y stuff. Otherwise, you plain old divide or reduce. So we're going to reduce the numbers. 1827, the greatest common factor is 9, so we would divide them both by 9. And so we would get 18 divide 9 is 2, and 27 divide 9 is 3. And then we would go to our x's, and here we're dealing with bases and exponents. When you divide with like bases, you subtract. 1 minus 1 is 0. We have x to the 0, which is 1. In other words, there's 1x on top and 1x on bottom, so the x's are gone. When we look at the y's, when you divide with like bases, you subtract. And so we say, well, what's the difference in the y's on top and bottom? And there's a difference of 3, 5 on top, 2 on bottom. And we say, well, where are there more at? And the answer was on the top. And so we put that y to the cube on top, and there's no y's left on bottom. When we get to the radicals, and I'm just going to kind of circle it in blue to separate it there, then we're just dividing names. Just like here, you multiply the radical names and get a new radical name. Then you would divide the radical name. Square root 15 divides square root 3 is square root 5. The bigger number is on top, so the square root 5 goes on top. And then we're going to shift the 3 to the middle of the fraction like that. 2y cubed square root 5 over 3. Any questions on number 3? Okay. Now, number 4, square root 24, does not have a perfect square root. And if we go to the formal definition of simplifying, then we say that we're going to rewrite it as the product of its largest perfect square factor and the other factor. Here's the factors of 24. 1 times 24, 2 times 12, 3 times 8, 4 times 6. Perfect square numbers are like 1 squared is 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16. The largest perfect square factor of 24 is 4, and we usually don't even use a 1. So we could rewrite the square root of 24 as the square root of 4 times 6. The square root of 4 is 2. Square root of 6 doesn't come out even, and so we get 2 square root of 6. That's the method of simplifying a radical, by looking at it as the largest perfect square factor of it and the other factor that goes with it. Now, what we learned on page 15 and 16 of this text, and then we picked up again in Unit 9.3, was to do the prime factorization. And so this is method 2. That would be to do the prime factorization. 24 divided by 2 is 12, divided by 2 is 6, divided by 2 is 3, and then rewrite it as the product of those primes, 2 times 2 times 2 times 3. And then we said if you have square root, you circle sets of 2, cube root sets of 3, etc. We're going to make a new radical. From each set, we'll bring 1 from the set out. What did not get circled, we'll put back in. We'll multiply anything on the outside together. We'll multiply anything on the inside together and simplify. And so there's the in your head method, if you can think of the largest perfect square factor, or there's the on the paper prime factorization method if you couldn't. Any questions on number 4? Okay. Number 5, cube roots could work the same. If we wanted to simplify this cube root, we could rewrite it as the product of its largest cube root factor and another factor. Now you may recognize 27 as being 3 cubed. 3 to the third is 27. And then 27 times 10 is 270. So knowing that, you could say, well, cube root 27 is 3. And so you're going to have 3 cube roots of 10. That would be the doing it in your head real quick method. We identified the largest perfect cube factor of 270, which was 27. If that doesn't just happen in your head, then we have a prime factorization method to use on larger numbers that don't work out in your head, or even smaller numbers that don't work in your head, which is fine. And so we would do the prime factorization method if that didn't work by doing the prime factorization. 2 will go 135 times. 3 will go into that 45 times. 3 will go into that 15 times. And 3 will go into that 5 times. And we would rewrite it as the product of its primes, not forgetting that little index 3. So we're going to have 2 times 3 times 3 times 3 times 5. For cube root, we circle sets of 3. We would make a new radical. From each set, we bring 1 out. What did not get circled in a set goes back in. We multiply if there's things to multiply, and we get 3 cube roots of 10. The same answer, whether we do it the prime factorization method or we can mentally think of the largest perfect cube factor. Any questions so far? Okay. Now we're fixing to get into a set of problems that make us have to think about the steps to simplifying a radical on page 248. This was also on page 15 of the text. It says to simplify a radical, you ask yourself these 4 questions in this order after every single step. And it might do us some good maybe just to go back real quick to page 248. And so I think I'll do that. I think we'll just back up here to page 248 so we can look at those real fast. To simplify a radical, you ask yourself these 4 questions in this order after every single step. Number one, will anything reduce? We got to think all the way back to page 5. We reduce numbers with numbers and square roots with square roots, and then we looked at that concept again at the first of this chapter. Number two, will a radical break down? That means, does it have any perfect square factors other than 1? Or when you do the prime factorization and you try to circle sets of 2, sets of 3, did you get any sets? If it has sets, then it'll break down. Question 3, is there a fraction in the square root? You can't have a fraction in the square root. And question 4, is there a square root in the denominator? Or cube root in the denominator, or fourth root? When you get no to all 4 questions, then it must be in simplest form. Okay, so don't forget that that's the steps, and you might want to refer back to that page as we're doing this lesson. You might want your book open to that and then be watching the video. Okay, so here we go. We're on number 6. So question 1, will a radical break down? No. Or question 1, will anything reduce? Will 5 and 6 reduce? No. Question 2, will a radical break down? No. Question 3, is there a fraction in the radical? Yes, there's a fraction in the radical. To make there not be a fraction in the radical, we just split it apart into the square root 5 divided square root 6. So we go back to question 1. Will anything reduce? No. Will a radical break down? Well, you may say, well, the 6 might. Well, we'll divide by 2 and 3. For square root, we need sets of 2. Is there a set of 2 2's? No. Set of 3 3's? No. So it won't break down. Question 3, is there a fraction inside the square root? Not anymore. Question 4, is there a radical in the denominator? Yes. So what we're going to do is rationalize the denominator, and if you recall, what we want to do is think about the primes involved in that 6, and we want to multiply by the square root of whatever it takes so that each of those primes appears the index number of times, and we know that if it's square root, the index is an understood 2. So we need there to be a total of 2 2's. We already have 1, so we need another one. We need a total of 2 3's. We've already got 1, so we need another one. And so we're going to multiply the top and bottom by the square root of 2 times 3, so that what we've done is created a pair of 2's when I put what I've already got with that, and a pair of 3's when I put what I've already got with that. We would do the same to the numerator to make it an equivalent fraction. What we have on bottom by creating this pair of 2's is a 2 that pops out, and by creating a pair of 3's, a 3 that pops out, and now there's no longer a radical in the denominator. What we're going to have in the numerator is square root 5 times 2 is 10 times 3 is 30, and so we get square root 30 over 2 times 3, which is square root 30 divided 6. Now we say, well, question 1, will anything reduce? Well, you can't reduce a square root with a number. So no, you can't reduce even though 6 goes into 30. 6 does not go into square root 30. Question 2, will a radical break down? You maybe think, well, that 30 might. Well, let's prime factor it out. You get a 2 and a 3 and a 5. Were there any pairs of primes? There wasn't 2 2's. There's not 3 3's. There's not 3 5's. So the radical will not break down. Question 3, is there a fraction inside that square root? No, there's a whole number. Question 4, is there a radical in the denominator? No, so that must be the answer in simplest form. Any questions on number 6? Okay. Question number 7. We begin by saying, will anything reduce? And when we think that, we think, well, we're going to reduce the number with the number and the name with the name, square root with square root. Three and 6 have a greatest common factor of 3, and so we're going to get a 1 and a 2 Square root 3 and square root 5 will not break down, so we're going to have a square root 3 on top still and a square root 5 on bottom, and that 1 is understood, and so we have square root 3 over 2 square root 5. And then we go back to question number 1. Will anything reduce? No. Will either radical square root 3 or square root 5 break down? No, they're prime numbers. Question 3, is there a fraction inside either square root? No, there's whole numbers in each of them. Question 4, is there a radical in the denominator? Yes. So we're going to multiply by the square root of whatever it takes so that the primes involved in 5 appear 2 times apiece. Well, there's only one prime involved in 5, and that's 5. And we've already got it once, so we need it one more time. So we're going to multiply the top and bottom by the square root of 5. And I'm going to move that other out of my way over there so I can just keep working across the board. On top, we're going to get square root 3 times square root 5 is square root 15. On bottom, we have a 2 that was already out there. And then for 5s, it pops out a 5. We go ahead and multiply, and we're going to get square root 15 over 10. We then go back through all of our questions. Question 1, will anything reduce? No, you can't reduce a square root with a number. Question 2, will the radical break down? The answer is no, because we have only single primes, a 3 and a 5, single 3, single 5. Question 3, is there a fraction in the square root? No, there's a whole number 15. Question 4, is there a radical in the denominator? No, so we got a no to all 4 questions, and so that radical is in simplest form. Any questions on number 7? Now, question 9 is a little bit more complex. What we've dealt with so far are things that are multiplied in the numerator and denominator, but on number 9, we have a plus sign. Now, when we have a plus sign that separates 2 terms, then what we have is a binomial. And there's understood parenthesis. Now, we learned through some investigation in our lesson on page 248 and 249, 250, that we have to handle this in a little bit different. When you have a radical in a binomial that you're trying to get rid of in the denominator, then you multiply by the binomial conjugate. And binomial conjugates are such that you have the same 2 items, but instead of having a plus, you have a minus. We learned about binomial conjugates in the textbook on page 204 of chapter 7. And what we learned is that the result of multiplying binomial conjugates is the difference between the 2 items squared. Now what that gives us is 5 squared, which is 25, minus square root of 6 squared, which is 6, because the square and the square root cancel. And then 25 minus 6 would be 19. And so what that does, it rationalizes the denominator. It created a whole number for the denominator. So you might need to go back and study chapter 7 just a little bit, page 200, and then go back and study where we did this back there in that lesson, lesson 9.3, page 248 to 250. What you do to the denominator, you have to do to the numerator, and so we must also multiply the numerator by 5 minus square root 6. Now, the numerators are not binomial conjugates, and so we have to do a little bit of work to get that. Here's the work to do that, and this work we learned on page 200. We called it fancy distributive property. Some people call it the FOIL method, which is different than the way I present it. I did present the FOIL method in my updated version of my textbook. What we would do here is we would take this first binomial and distribute it through the second. Now this is following order of operations, not using a trick. So we're going to have 3 plus square root 6 times the first little piece 5. And then we're going to have 3 plus square root 6 again times the second little piece negative square root 6. And don't forget to carry the minus as a sign. We then distribute again. We're going to have 5 times 3 is 15. 5 times square root 6 is positive 5 square root 6. Negative square root 6 times 3 is negative or minus 3 square root 6. And negative square root 6 times negative times positive square root 6. Square root 6 times square root 6 is 6. When you multiply with different signs, it's negative, and so we get a minus 6. And you can see that I messed up. Man, I'm sorry about that. This is a square root 2, and that should have been a 2. And this should have been a 2. And so this should have been a 5 square root 2. And here to here should have been a square root 12. Square root 12 will break down. 2 will go into it 6. 2 will go into it 3. You got a pair of 2's, and so you would have a 2 square root 3. So if we replace square root 12, I'm just going to erase it and replace it. Then we're going to have a minus 2 square root 3. Now I'm going to clean that up, plus 5 square root 2. So here's what we have. None of those are like terms, and so that becomes our numerator, 15 plus 5 square root 2 minus 3 square root 6 minus 2 square root 3 all over 19, and we would shift our 19 to the middle. Any questions on number 9? Sorry about grabbing the wrong number there as I distributed the first binomial through the second. Okay. Well, we're going to make that the first half of our chapter review recording, and we'll do the rest of the recording on part 2.